Hi, smelly chickens. Welcome to your pre-calculus lesson. It's going to be lesson, sorry for the glare, 17.1, first part of lesson 17. We're going to be covering examples 1 to 3 today. So actually, there'll be the first objective and part of the second objective. Just so you know. You've already done the pre-reading stuff in the your study notebook. So you may have written something like that down already. If you've got your study notebook, it's page 15 that I had you go ahead and do. So I'm going to look at that first because I want to make sure that the vocabulary you got is the vocabulary that you need, and the two things that we're going to do today. So as far as objectives go, we're going to find inverses of functions, and well, first we'll talk about what an inverse is and how it plays, and then today we're gonna algebraically find what the inverses are. We're going to verify that two formulas are actually inverses, and we're gonna use the calculator to just help us, but that's more of the next lesson, is verifying things or using the calculator to determine whether two functions are inverses of each other or not. So today we're going to find how to find inverses of a relation, and then secondly would be finding out if they are functions or not, and putting them together to follow a particular rule with inverses to prove algebraically that yes, they are inverses of each other. So under your vocabulary, they asked you to define domain and range in your own words. They said you could go to lesson 1.1. You probably just listed the way that it's listed there. It would be something like the domain are all the inputs of a relation, all the numbers that you put in, and the range are all the numbers that come out. The set of all the outputs, input, output. And what we're going to do today with a function is, with inverses, is we're going to put numbers into a function and get a range. We're going to take the values in the range and we're going to reverse engineer it, go through an inverse function back over to that domain, the range of the original function. We'll draw you a picture for that at some point. There's a thing in the book on page 66. Pictures that. New vocabulary. Domain and range are old concepts. New concepts would be inverse relations. If a function passes the horizontal line test, then it is said to be 1-to-1 because no x value is matched with more than one y value. No y value is matched with more than one x value. That's the key. We've said before that functions, you could plug in an x and get a y, right? You could plug in two different x's and get the same y, like on a parabola, but never could you plug in one x and get two different y's. Does it make sense? Hope so. So we have parabolas, that's good. X negative 2 would equal 4, and x of 2 would equal 4. That's fine. But if we got two functions and they're inverses of each other, it has to be a 1-to-1 both directions. There can only be one line going to or from a number in the x category of numbers and from the y category of numbers. I'll try to demonstrate that with taking a parabola and finding its inverse, which is not a function. Inverse functions. Two relations are inverse relations if and only if one relation contains the element BA whenever the other relation contains the elements AB. So there's share points that are just inverses of each other. All their points are inversed, are switched. The x's and the y's are switched, mapped out. That would be one way of graphing out or explaining. I guess you could have a function and its inverse having the same sets of ordered pairs, but the x's, all the x's and the y's have been switched. And then lastly, if the inverse relation of a function is also a function, then it is called the inverse function of f. Similar to matrices, not all functions have an inverse. Remember, with matrix, if it has a determinant of 0, then it doesn't have it doesn't have an inverse, and we call it a singular matrix. It's the same thing that can happen with functions. You're going to have a function, try to find it in its inverse, but its inverse is not a function. In a sense, there's a singularity to it. Parabolas are like that. So there will be a place where I'm going to ask you to like stop and write some stuff down. We'll get there. We're going to start with first concept of the horizontal line test. Now, that's not what we've done before. It sounds almost the same. In the past, we've had the vertical line test to test to see if something is a function, if a relation is a function. But today we're going to use it to test a function. If it passes this test, then it also has an inverse. It also has an inverse. And we're going to be using the expression f to the negative 1 of x. So we say inverse function when we do this, okay? That thing right up there doesn't mean we're going to take the reciprocal. It means it's just a symbol for the inverse of a function, inverse of function f. Okay, so if we just take something like a line, linear function, and we think about it drawing a horizontal line through this thing. You get my horizontal line here. I can cut through that line anywhere with a horizontal line, and it only cuts through my graph once at the most. And so that is my indication that this function does have an inverse. It passes the horizontal line test. Its inverse will pass the vertical line test. That's the first key concept there. A function has an inverse function, f to the negative 1, if and only if. So it has to pass this condition, that each horizontal line intersecting the graph of the function is at most 1 point. So as an example, since no horizontal line intersects the graph of f more than once, the inverse function does exist. This, whatever its equation is, it does have an inverse equation that you could graph out. That would also be a function. So let me give you an example of a function that doesn't have an inverse. F of x equals x squared. Or I'll make it a little more complicated and we'll go x squared minus 4. Y equals x squared minus 4. Okay, I think we know what the graph is. Parent function x squared. And we drop it down 4 places. So we would have symmetrical parabola down here, negative 4. Now, following the definition here, they're saying that let's take a horizontal line and let's go across this function, and right there it touches at 1 place, but anywhere else above here it's going to touch at 2. And it has to be at maximum 1 place where it cuts through. So because if I drew a line through here and it cuts through the parabola through the parabola there and there, if I went to find the inverse relation of this, it would not pass the vertical line test and be a function. So what would that look like? Well, the inverse of this function would be taking the x's and the y's and making them trade places. So the inverse of y equals x squared minus 4 would be x equals y squared minus 4. Now I can't graph that on my calculator, but Desmos does graph that. And let me show you what would happen there. Again, if you've got it on your phone, that is super cool. Where you go and check it out on your calculator. So there we got a parabola, and then I graphed its inverse of, and I could just type it in as x equals y squared minus 4. And it makes a sideways parabola. I've also drawn in the line y equals x because that's kind of like the dividing line between the two, and if you tilt it sideways, like 45-degree angle, it should look the same on the left as it does on the right of the line y equals x. We already said that all the x values get switched to y values and all the y values get switched to x values and then plotted. So it makes a sideways parabola that's going to not pass the vertical line test. Okay. Now, if you try that on your calculator, if you go ahead and you want to like take the equation x equals y squared minus 4 and make it so that your calculator will graph it, you're going to have to go x plus 4 and then take the square root. So maybe your y2 would be the square root of x plus 4. So I already did that on my calculator, and what happens is I only get like half of that sideways parabola, because it doesn't account for the fact that the square roots could be plus or minus. If I do that, it really only graphs this part. That would be plus square root of 4 plus x. And then if you also went in and typed in another one of minus negative square root of x plus 4, you'll get the other half of the parabola. So the calculator knows that's not going to be a function. It can only graph functions, at least in function mode. If you go to parametric mode, you can get it to do sideways parabolas. But in our regular mode, it's only going to give you half of it so that it's going to pass the vertical line test. But technically, this inverse function, well, this inverse relation is a sideways parabola that will not pass the vertical line test, because the original function, the parabola, cannot pass the horizontal line test. So it's kind of like when we were doing discriminants with quadratic equations. If the stuff underneath the square root sign ends up being negative, then we know something about our answer. If it's 0, we know something about our answer. If it's a positive, we knew something about our answer. This is a way of knowing something about the inverse. We take the original equation, we do this horizontal line test. If it fails the horizontal line test, its inverse will fail the vertical line test. So it gives us a picture to try to explain what would happen. That could be helpful. Sometimes it feels like it might be confusing. But let's say that we have 1 over x as our function. We graph that, and we have this. If I take my stick, I can cut through at most one place everywhere, even that place there's actually no graph right there, but that's still less than 1. So there's nowhere where I'm going to cut through more than 1. This one has an inverse. Y equals 1 over x. The inverse is x equals 1 over y. Anyone know what that looks like as a graph? That's what it looks like as a graph. It looks like itself. It's the same graph. They're actually, it's kind of a weird one. Its inverse is identical to it. Maybe we had something like, how about something like this? We get some type of cubic. Is that going to pass the horizontal line test? Bethan's shaking her head no, because already the axis is cutting through it in 3 places. So, now, if we do its inverse, which would be x equals y cubed, we would get something that goes this way. It would go like that. And definitely not going to pass a horizontal line test. So that one would fail as having an inverse. Doesn't mean it's bad. It's just only a relation, not a function. Yeah. We can't have like strong feelings about functions sometimes. You're bad. I don't like you. Well, you may not like it, but it doesn't really matter. Okay, so that's the first thing. Finding inverse functions then, like actually getting the formula for these things, is going to require a little bit of algebra. Now, I could just draw the picture of it, but that's not telling me, and I could write a formula, but I still got to massage it a little bit to get the actual function out of it. So, here's what we got. We've got x's and y's, right? We've got domains and ranges. And for a function to have an inverse, this kind of setup has to be true. Every element in x, in the domain, has to have one corresponding element in the range in y. This is the only kind of situation where we can have inverses, because not only are we going to travel through a function this way, but we're going to travel through an inverse function this way. We have to be able to take our inputs and get outputs, and then to take our outputs and plug it into a different equation and get the inputs. So this kind of setup has an inverse because it's got a one-to-one correspondence of x's and y's, of inputs and outputs. Here we got domain range. Over here, going this direction, we've got domain and range. The domain of this function ends up being the range of this function, and vice versa. The range of this function ends up being the domain of this function. They have to play nicely. I'll show you what doesn't work. This type of situation where two different values of x equal the same value of y. And that would be like a parabola. That's usually not a problem. It's not a problem going this way. We could plug in a -2 and get 4. We could plug in a 2 and get 4. We can plug in a 1 and get 1. That's fine. That direction, that's okay for having a function. But, make sure we see the whole thing over here. But if we were going this way, and these are our x's and these are our y's, then we have a problem. 4 cannot be plugged in and get two different answers in the other direction. That does not work. So we'd say here, this does not exist. An inverse function here for this function, we can go this way, but we can't go back. We can't go back without breaking the one-to-one correspondence. This is a 1-to-2 correspondence. So that would not be a function. Apply the vertical line test. Let's find the inverse then. I think we did a little bit of this in Algebra 2. If you've got a moment, maybe you should pause and write down the step 1, 2, 3, 4 business there on page 66. This gives us a 4-part algorithm for going through to find the formula for the inverse of a function. I'll read it out loud, but you can hit pause and you can write them down one at a time. But this is definitely go in your notes. So step 1, determine whether the function has an inverse by checking to see if it's 1-to-1 using the horizontal line test. I'd say step 1, apply the horizontal line test. Sorry. Step 2, in the equation for f of x, replace f of x with a y, and then switch x and y. In the equation for f of x, replace f of x with y, and then interchange x and y. We'll demonstrate that with some easy functions. Step 3, solve for y, and then replace y with f to the -1x in the new equation. So switch x and y, do some math, and then put f to the -1 back in there where y goes. And then step 4, look at it and see if there are any restrictions on its domain. Make sure that it's a 1-to-1 correspondence. It says, then show that the domain of f is equal to the range of its inverse, and that the range of f is equal to the domain of its inverse. All the x's and y's have to be interchangeable. Okay? All the x's and the y's from the original function have to be able to be switched and be all the set of values that are going to be on the other function, the inverse function. While Bethan's scribbling the stuff down, I'll put some examples up here on the board and try to walk you through these, how we would go through the stages to get an answer. I'm going to start with, I'll start with something easy. Well, actually, they start with like f of x equals. And then I'll do 3 other ones here, the guided practice ones. We're going to have to do some algebra. The do unto one side as you do unto the other kind of stuff. Step 1, we check the vertical line test. Well, this is just a line, so it is going to have an inverse for sure. We can proceed. Now, if it's not, we should just stop. We're not going to have a function. We might have a relation, but we're not going to have a function. This one has an inverse function. Step 1, replace f of x with y. Actually, that's like step 2. Step 3. Step 2 still. We're going to switch x and y in the equation. So, if it's a y, we replace it with an x. And then where there's x, we put a y. We're then going to solve this for y. So y would equal x minus 2. And then lastly, we're going to replace the y with f to the negative 1 of x. So there's our inverse function, x minus 2. So we got x plus 2. Its inverse is x minus 2. And if we're graphing it, one of those lines is x plus 2. The other one's x minus 2. They're inverses of each other. If we're to add them together, they squeeze in on each other. Okay, so that's the process that we do to get the inverse function. Let me give you one that's a little bit more complicated. I'm going to do the guided practice 2A at the bottom of 67. There's other examples that you could look at there on page 67 for finding inverses. And again, we're doing this algebraically. So I'll give you this one. F of x is negative 16 plus x cubed. Okay, so first it says we should check it to make sure that it has an inverse by graphing it and seeing if it's going to pass the horizontal line test. That way we know that its inverse will pass the vertical line test. Okay, plus x to the third. Negative 16 plus x to the third. We'll graph it and we'll see what it looks like. Let me go down there and find where it crisscrosses. I go to negative 20 on the on the y-axis. Okay, so here it comes. Okay, it looks like, and there's y equals x. It appears that I can draw a horizontal line through it and it'll be fine. At every place that I could possibly draw a line through it. Again, I'll show you that. You can do it on your own calculator. Here we go. So I think we are allowed to proceed. We replace f of x with y. We then switch where x and y are located. So x equals negative 16 plus y cubed. We're going to solve for y. So that'd be x plus 16 equals y cubed. We'll finish that off by taking the cubed root of both sides. And then lastly, we're going to replace the y with f to the negative 1 of x. The inverse is the cubed root of x plus 16. Now, if you're curious, you could go ahead and graph that one. Keep your original on there. And then this time we're going to ask for the cubed root. We can go alpha f2. And they have a number 6. Alpha f2 is a whatever of root power. So we'll go the third root of x plus 16. I want to graph it. I want to make sure that, yep, looks like a function. It'll pass the vertical line test its inverse would. All right, now I want you to think about what happens. Basically, inverse functions do everything that we did to the original, just in reverse order. the first thing we would do is once we plug in x is we're going to cube it, and then we're going to take away 16. That's what we would do if we plugged in x into the original function. We would cube the number and then take away 16. This time, if we plug in a number, we're going to add 16 to it first and then take the cubed root. So it's the two operations that we do up here, we use their inverse operation in the inverse order, in the opposite order to get the new equation, the cubed root of x plus 16. That's why they're inverses. If I plug a number in here, it does stuff to it, and then I plug a number in here, it does the opposite thing to it. So I'll get back basically to where I started. Any x, y that I plug into this equation is also a point y, x in this equation, a point on the graphs of these things. They would share that point there. And any x, y point, we switch it, and it will also be in the domain or range of the second one. Okay, that's the process. Let's do a couple more. Start off with f of x. This one's a rational function, x plus 7 over x. Step 1 is to replace f of x with y. Second step is to replace x's with y's and y's with x's. So switch where they're located here. This will be a y plus 7 over y. And then we're going to solve for y. I'm going to multiply both sides by y and get yx equals y plus 7. I got to put everything with y on one side. So let's take this y and subtract y from both sides. Yx minus y equals 7. Factor out the y. Solve for y. Y would equal 7 divided by x minus 1. And then to finish off, can you see that? Nah. To finish that off, we're going to replace the y with f to the negative 1 of x. So here's our original. Here's our f of x. And then here's our inverse function, 7 over x minus 1. Now, I knew this was going to be okay to draw a line through it. I know this is going to be okay. I can draw a line through it because the parent function is the way that one will jive. Okay, now think about these two. If I plug an x in here, plug a number in for x, I do two things. I add 7 and I divide by the number. Add 7 and divide by the number. Here, I plug in a number and take away 1 and then take 7 and divide by that number. That doesn't seem like it's doing the opposite, but I could write this in a different way that I could show you that that thing is true. If we looked at the pictures, this is where a picture comes in handy because formula-wise, I'm not sure that it's going to work. And of course, this one won't be true anytime that x is 1. This one wouldn't be true anytime x is 0. So we have to watch out for like where places are going to have holes that we could expect or breaks, discontinuities. So this is nice only if I did all the math right. The picture will help me verify whether they are actually inverses of each other, but that's for the next episode. Okay, I do one more of this kind of algebraic check, and we'll have f of x equals x squared minus 20. So think, I plug a number in for x, I square it, I take away 20, I take the square root. Maybe you can think of what would be in the opposite direction. If I'm thinking through it, I'm thinking I should be able to take a number, square it, then what comes next? Add 20, and then take the square root. I think this is only half of the thing. Let's see what happens. Y is square root of x squared minus 20. Switch the x and the y, so x equals the square root of y squared minus 20. I'm going to solve for y. So I'm going to take the square both sides. X squared will equal y squared minus 20. And I'm going to solve for y, so I'll get x squared plus 20 equals y squared. And I'll finish it off by taking the square root of both sides. And it is what I thought it would be. There's our inverse, f to the negative 1 of x. So this thing and this thing are doing the opposite things. I'm just reversing the order of all the operations that I do to it. Again, square it, take away 20, square root. Square root, square it, add 20, square root. Picture-wise, I don't know what they would look like, but inverse-wise, formula-wise, that's how I'm going to find the algebraic formula for the inverse. Let's see. I've got third thing, composition of inverses. All right, this is an important thing. We've already done compositions, right? We've said, let's take this formula and plug it into the other one and put them together. So this third thing here, composition of inverses, says that if and only if, which in math we do this, if and only if, okay, two functions are inverses, if and only if you can do both of these things. And g bracket g of f of x equals x. That means you have to be able to compose these two equations, and out comes y equals x. Out comes y equals x. Or you get x, just the line x, right? So I'll take this first one here and see if I can do it with these two functions. Let's plug in this equation into this equation. So I'm going to leave a space there for squaring. I'm going to take this equation and plug it in here. So I'm like, okay, I'll take the square root of x squared plus 20 and plug it into this equation and see what we get. I'm taking the square root of a square, so the square root and the square will cancel each other out. So that's what I got. I've got 20 minus 20, so that cancels each other out. That leaves me with the square root of x squared, and that is x. So that way works. And then I got to try it the other way too. I got to take this equation and plug it in here. So I'm going to leave space for that. And I'm going to plug in the square root of x squared minus 20. You see, this is going to work the same way because I'm squaring the square root. So this part cancels each other out. I've got plus 20 minus 20, so that part cancels each other out. I got the square root of x squared, and that's the same thing as I had before. Both compositions get me to x, and that's like your test to make sure that your two equations are actually inverses of each other. Both of them have to work. You have to compose the two and get x. Similar to like matrices. How do I know that this thing, putting two things together, I get the identity matrix. This is the identity function. F of x equals x is the identity function. So I'll go back to one of the last examples where we got one function being x plus 7 over x, and its inverse was determined to be 7 over x minus 1. I'm going to compose these two together. I'm going to take this one and put it into there. So it'll be 7 over that function minus 1. X plus 7 over x minus 1. It's a little yucky because in order to subtract these, I have to have like a common denominator. So I'm going to call this one x over x. And then I can do the subtraction. X minus x plus 7 over x. That's 7 divided by, whoa, that's a big 7. 7 divided by 7 over x. Rule for fractions say that I can multiply the top and bottom by the same thing. And all this becomes 1, and up here, 7's cancel out, and look what pops out. X. Surprise! Well, that's how I can make sure that I did my math right, is if this works this way. Okay, that's doing it one direction. Here's the other way. We would take 7 over x minus 1 plus 7 over 7 over x minus 1. Oh my goodness. Okay, I'll do the same problem set up here where I need a common denominator. 7 over x minus 1. I need to do this one as a x minus 1 over x minus 1. So here I'll get, combining this stuff, I'll get 7 plus 7 times x minus 1 over x minus 1 over 7 over x minus 1. If you remember things about fractions, if both these fractions are over the same thing, the over the same thing can just be ignored. So now here's our fraction. 7 plus 7x minus 7 over 7. Those 7's are going to cancel each other out. I got 7x over 7, which is x. The two compose both directions, and I get x that pops out of the whole thing at the end. So those are inverses. I can prove algebraically by composing them in both directions, plug this one into that one, plug that one into this one, that they share a set of points, x, y's over here. All of these are y, x's. I'll do, no, I'm not going to do that one because I don't want to cube stuff. I'm just not going to do that one. Algebraically, no thank you. So there you go, examples 1, 2, and 3. Verifying inverse functions. We have to be able to compose them into each other and get the same answer. The identity function y, or y equals x is the easy way to explain it. Homework. That's the last thing I got to tell you. 1 through 20. Numbers 27 to 30. And then one brilliant question. You guys have been doing a good job. The questions thus far. Keep up the good work. It would be best if you could submit that somehow to me by Friday at noon. That way your hands are clean and your heart is pure. And you can walk away from math for a whole week. So that's what I'm hoping from you. Lesson 17.1, inverse functions, 1 through 20. 27 to 30 plus one question that has something to do with this inverse stuff. Think up something kind of creative, if you would, please. Okay, thanks for tuning in, and we'll talk to you soon.